Yes, so I'm just going to make a little announcement to those of you here. Some of you will know Jifeng He, who worked in Oxford and then moved back to Shanghai. 10 years ago, he had a 70th birthday festschrift celebration in Shanghai, and he's still going very strong. So we're now going to have an 80th birthday festschrift in Shanghai, but this time it's going to be hybrid. And I'm hoping that we're going to be able to give access to FACS members to listen to talks on Zoom. So it's going to be on the 15th and the 16th of September in the morning, so it fits in with Chinese time. And so there'll be information on it on the FACS website. We don't know exactly if we have to limit numbers and so on at the moment. So we'll obviously advertise that on the normal FACS mailing list as well. So also, we will to give free access to the proceedings, which are going to be in LNCS 14080. So they're with Springer at the moment. So they'll be available free for about 4 weeks around September or so. So again, we'll put a link from the FACS website for that for anyone who just wants to download the proceedings. We've got some quite good speakers like Moshe Vardi and Ian Hayes, Jim Woodcock, etc. But essentially, there's about a day's worth of talks. I think we've got about 15 or 16 talks of half an hour each. So hopefully, you'll be very welcome to come and listen to that. Watch out on the BCS website, the FACS website. Thanks, Elvira. I'll pass back to you.
Thank you. Okay, so yes, thank you everyone for joining, and thank you, Claudio, for agreeing to present this talk. So Claudio is an assistant professor at the University of Bergamo, and he works on software engineering and formal methods with a special focus on cyber-physical systems and robotics and formal verification. And Claudio works closely with industry, as I understand. In particular, today he's talking about topological proofs, which I'm very curious to learn what they're about. So if you want to start, thank you.
Okay, so thank you everyone for being here. So the title of this talk is the Independence Day of Witnessing the Correctness of a System from Topological Proof and Beyond. Second, okay, good. So basically, this is our agenda, or briefly what I will discuss in this talk. Essentially, I will go over 4 different papers, which of course are related, are closely related. The first one is titled From Model Checking to a Temporal Proof for Partial Models. It appeared in 2017 at the International Conference on Software Engineering and Formal Methods, SEFM. The second paper is Integrating Topological Proof with Model Checking to Instrument Iterative Design, appeared in 2020 at the Fundamental Approaches to Software Engineering, FACS. Then there is TOrPEDO, Witnessing Model Correctness with Topological Proof, which appeared in 2021 in Formal Aspect of Computing. And finally, I will briefly go over the paper Trace Diagnostic for Signal-Based Temporal Logic for Temporal Properties, which appeared in 2023 on the IEEE Transaction on Software Engineering. And I will conclude my talk with some reflections, lessons learned, and actually some speculation from my side. So let's start from the work of 2017. This work has been done in collaboration with Bernasconi Anna, Spoletini Paola, Leonard Zach, and Carlo Ghezzi. But actually, this work started many years before. It started in 2001 from this work done by Doron Pellet and Leonard Zach, with title From Model Checking to a Temporal Proof. Essentially, what these two authors did is that they realized that model checking and Turing proving are 2 techniques that help designers to developing software that are correct in 2 complementary ways. So the first one is model checking. So model checking, given a model of the system and the property of interest, verifies whether the property holds in the system. So it returns yes if the property is satisfied, or no plus a counterexample if the property is violated. Actually, the useful information provided by the model checking is the counterexample, because it can be used by the developer to understand why the property is violated and therefore to improve the model. TOrImproving, on the other side, it takes a model of the system and property of interest. It returns yes plus a proof if the model is satisfied and no in the opposite case. And the interesting information here is the proof. The reason being that the proof explains to the final user why the property is violated, and therefore it can be used for by the developer to improve the model. So essentially, the developer can understand why the property is violated and if why the property is satisfied. And if it is satisfied for the wrong reason, it can actually improve the model. So essentially what Leonard Zak and Doron Pellett did, they tried to combine the two frameworks. They define a combined framework which basically combine the benefit of model checking and TOrImproving. So actually the combined framework, it produces a proof if the property is satisfied, and it also produces a counterexample if the property is violated. So the underlying assumption of this work is that the model of the system is completely specified. Essentially, the model is a definitive model. So back then, what I was doing and I was working on during my PhD was on the verification of models that are partially specified and incomplete. So these models are often present in practice. So they are largely studied by the formal methods community. They started from the work of Kim Larsen in 1988, from some work of Godefroy, some work of Goldfinker, Marcia checking, and finally some recent work we also proposed. They have been also studied by the software engineering community, with many work on software and system modeling, ICSI by Chechik, or some additional work of Sebastian Unchiter. And finally, they are also extensively studied in the requirement engineering community, with many work that supports decision-making in presence of uncertainty, or combine basically requirement engineering techniques and develop techniques to support the development of, just give me 1 second because the presentation is moving forward independently by itself. So essentially, we arrive at this point. So partial model has been extensively studied. Let's consider one simple example of a partial model. This is a partial Kripke structure. Essentially, is a labor transition system. So it has 3 states: state as 0, state as 1, and state as 2. There are propositions, essentially the proposition green, the proposition red. So this basically example represent a light traffic control. So essentially you have these 2 lights, the light red and the light green, which can be on and off depending on the state. For example, in state S1, the green light is on and the red light is off. As you can see from the visual explanation, the green light is on. In state S0, the red light is on and the green light is off. But for example, you may be uncertain about the value of some proposition in some of the states. For example, in state S2, you don't know the value of the green and the red light, meaning that the designer still has to decide whether this light will be on or off in those states. And of course, the designer can refine the model. For example, it can specify that the green light is on in state S2 by turning on the value of the green light in some of the revision of the model. And of course, even if the model is incomplete, you may still want to verify this model. So even if you have this incomplete elements, this question mark in the system, you may want to verify your properties. So for example, you may want to verify that if in your system the red lights up infinitely often, so globally finally red, or the green lights up infinitely often, so globally finally green, or when the light is red, it will always be green, which is a requirement presented in this slide, which is wrong on purpose. So our question and the goal of this work is to design a technique that helps designer in producing correct software by combining model checking and theorem proving, and specifically by focusing on partial model. Actually, this idea came by the fact that Anna Bernasconi spent a period at University of Chicago, Illinois, where she met Leonard Zach. She knew Paula Spolettini. So we started this collaboration with the goal and the intent to extend this framework to the three-value context, where model can actually be partial and incomplete. So, and here is basically our contribution. Our contribution of this work is Thrive. Thrive is a verification framework for partial model. It's basically represented in this system. The framework takes as input a model of the system and a property of interest. So the framework is a general framework and a high-level framework, which can be customized over different modeling formulae. And later on, we will see how this framework customized to specific modeling formulae. So the main idea is that when you have a partial model and you run the model checking tool, you may be in the situation where the model, even if it's partial, violates the property of interest. So there is a violation, and the violation is present regardless of the unknown parts present in the model. So in this case, you want to return to the user a definitive counterexample. Essentially, an information that explains to the user, even if the model is violated, it's partially specified. Here is a trace that shows that the requirement is violated. For example, if we consider our partial paper structure of the semaphore, and the requirements, when the light is red, it will always become green. So globally red implies globally green. This property is violated. Essentially, the reason that if you keep looping between S0 and S1, globally green will never be satisfied, because in state S0, the green light is on. Note that this requirement is formalized not in a precise way. Actually, the formalization of the textual explanation is wrong, and this was done on purpose for explanation reason in the paper. But the point here is that this property is violated. Even if there are unknown parts of the model, the property is still violated, and for this reason, what the framework would Thrive should return is a definitive counterexample. Kind of an information showing that by looping between S0 and S1, the property is violated. The second case is where basically the satisfaction of the property depends on the unknown part. So in this case, you may want to return what we call a proof and a possible counterexample. So the proof basically shows that there is a way to make the system satisfy the property. So you can refine your system in a way that satisfies the property. And the possible counterexample, it does the reverse. So it shows that there is a way to refine the system that makes the property violated. So it basically explains the two factors to the user, how to make the property satisfied and how to make it violated. So if we go to back to our running example, we can see that if you want to verify that the green lights up infinitely often in the system, this property is possibly satisfied. The reason is that it depends on how we turn the green light in state S2. So if we turn the green light on in state S2, the property is satisfied. So the green lights up infinitely often in the system. But on the other hand, if we turn the green light off in state S2, the property is violated, because we can infinitely loop over state S0 and S2 without turning up the red light off ever. Let me stop 1 second and restart the slideshow, because it kind of moved back and forth by itself. So that's not good. Okay, we were here, right? So we have seen the possible counterexample. The final case is when the property is actually satisfied. So we actually, even if the model is incomplete, we can claim that the property is satisfied. We can provide a proof that regardless of how you refine the system, the property is satisfied. For example, if we consider the property that the red lights up infinitely often, and this partial keeper structure, this property is satisfied. Because sooner or later, we will always come back to the state as 0, where the red light is on. So this property does not depend on how we set the value of the true and the false proposition in state S2. So this property is satisfied. So this is the general framework. Of course, we have to instantiate the framework over by considering one modeling formalism and one type of property. So for the model of the system, we selected partial Kripke structure. Why we selected partial Kripke structure? Because they are formalisms which are typically used when you are defining theoretical work over 3-value systems. So if you look at the research literature, typically the theoretical result were presented on partial Kripke structure and then applied to other formalism like modal transition system or different type of formalism. We selected as a formalist to specify the properties of interest, linear time temporal logic, because with CTL is one of the two logic which is mostly used by the formal methods community for to be verified over Kripke structure or partial Kripke structure. So when we consider partial Kripke structure and linear time temporal logic, we can actually have two semantics. The first semantics is called the 3-value semantics. It is based on the information ordering. So essentially, the intuition is that true provides more information than maybe, and maybe provides more information than false. The second semantic is the for semantic, which is based on the notion of refinement. And both of those semantics have advantages and disadvantages, which I will discuss in this slide. So the 3-value semantics is typically faster to be verified, meaning that we can check a property over the satisfaction of a property over a partial Kripke structure by just running twice a classical model checker. But the result is kind of not correct for the maybe cases. What I mean is that when a property holds with respect to the 3-value semantic, actually the property holds, the result is correct. When the property does not hold with respect to the 3-value semantic, it does not hold, so the result is correct. The tricky case is when a maybe value is returned. Intuitively, what a person expects is that there exists a way that to complete the partial Kripke structure that satisfies the property, and another one that violates the property. And this is not true. This is not true for the 3-value semantic, meaning that in some cases, even if the value returned is a question mark, is maybe, you may end up in a situation where all the refinements satisfy the property, or vice versa, all the refinements violate the property. So for this reason, the for semantics was proposed. This, of course, it's lower to be verified because it entails a satisfiability problem, but it returns a correct result. What I mean by correct is not correct under the formal method definition. It's just that it follows the natural intuition also for the maybe case. For the true and the false case, they are both correct. So for our instance of tribe, we consider the 3-value semantics. Why we consider the 3-value semantics? Because it basically relies on classical model checking techniques, which is what it was actually extended by the framework proposed by Pellet and Zach. So how does the 3-value semantic work, actually the model checking technique for the 3-value semantics? Essentially, given a model of the system, which is incomplete, the procedure for verifying the property behaves as follows. So first, I compute a pessimistic approximation of the model. Essentially, what I do is I do my best to violate the property. That's what the pessimistic approximation is. I take the model, which is incomplete. I change the model by doing my best to violating the property. If the property is satisfied, it means that actually, even if I tried my best to violate it, I wasn't able to violate the property. It means I should return a true value. The property is satisfied. And that's why you see the top result. So in the second case, I basically compute an optimistic approximation. So which means I do the dual exercise. I do my best to satisfy the property. If the property is not satisfied, then there is no way to satisfy the property. It means actually the property is violated, I return a false value, and that's my counterexample. In the opposite case, if none of the two previous conditions are satisfied, it basically means that I cannot conclude neither that the property is satisfied or nor that the property is violated. So this is the three-value model checker we selected. We adapted it to kind of fit with the Doron-Pellet and Leonard-Zook framework, where we basically modified the deductive verification framework they proposed to handle basically quick destruction. So we slightly changed the procedure to identify failing state and how the deduction rules work, because they were proposed on failed transition systems, so a different model. So what we ended up is desistance of thrive. So essentially what our procedure does is, starting from the model, we first compute the optimistic approximation. We run the two-value model checker. If we find a counterexample, then it's a definitive counterexample, and we return it as output. Now, vice versa, if the property is satisfied, we run the Turing prover and we compute the possible proof. Then we compute the pessimistic approximation. We run the two-value model checker. If we find a counterexample, we return the possible counterexample. If we do not find any counterexample, we run the theorem prover and we return the proof as output. Let's do this with a simple example with our semaphore. So let's start with the property phi3. So the property phi3, it says globally red implies globally green. So let's compute the optimistic approximation. So we do our best to satisfy the property, which is we turn both the red and the green light on state S2. And we run our model checker. So our model checker, it returns a counterexample. The reason is that, for example, by looping over state S0 and S1, the property is violated. So there is basically no way to improve our system. The property is and will remain violated, whatever refinement we propose for the state S2. Second case, we want to check that the green lights up infinitely often. So we do the optimistic approximation. So we turn the lights green and red on state S2. We run the model checker. Actually, the property is satisfied, which means we run the Turing prover and we have the proof. So this proof is computed by using the Pellet-Zach system I was mentioning before, and it's saved to be shown by the user. Then what we do is we compute the pessimistic approximation. So we turn the red and the green light off on state S2. We run the model checker. The model checker produces a counterexample. And in this case, the counterexample is that by looping on state S0 and S2 infinitely often, the property is violated. And we return these two artifacts to the user. Essentially, we have a possible proof that explains how to make the property satisfied, and a possible counterexample that explains how to make the property violated. Final case, it's basically the case in which we have globally finally red. We do the same exercise. We compute the optimistic approximation. We turn the lights on. We run the model checker. The property is satisfied. We compute the proof. And then we do the reverse. We compute the pessimistic approximation. We run the model checker. Again, the property is satisfied. And basically, we can run the theorem prover, have the proof. In this case, the system satisfies the property. We return the property the proof as out. And this helps the engineer in understanding why the property is satisfied. These are the three possible cases. Now, let's zoom back a bit about the tree value and the for semantics. As I was mentioning, our results are correct and our framework is designed over the tree value semantics. So for the case in which we return a maybe value, actually our results could in principle not be correct considering the for semantic. However, there are a set of aspects to be noticed. So the first one is that in many practical interesting cases, the for semantics is not more precise than the tree value one. So even if the tree value is less precise, that there's by consulting results from the literature, this does not happen often in practical cases. Second, there is a subset of LTL formulae, which are known as self-minimizing, for which the result of the tree value model checking is correct, meaning that is consistent. The result under the tree value semantic is consistent with the for semantic. In addition, most of the LTL patterns proposed in the literature, so the Dwyer patterns, are expressed and can be expressed using self-minimizing formula. And there are some constraints or sufficient condition that is satisfied, then they guarantee that the formula is self-minimized. So we acknowledge that this framework is not correct with respect with the for semantic, but this does not represent a serious limitation in practical case based on results from the literature. So what we did is then we conducted a preliminary evaluation. So our goal was to analyze how effective is Thrive with respect to incremental development. And what we did is actually a manual exercise. So we tried to manually simulate the design of a critical software system. And the system is actually a system used by physicians to check visual problems within patients. So we consider three properties that the system has to satisfy. We designed this property by consulting property specification patterns. We created an abstraction of the final model, and we check how Thrive supports incremental development. This was done manually. For one of the property, we actually found a definite counterexample showing the reason for the violation. Actually, the reason was that the property was wrong, not that the model was not correct. For one of the property, we actually understood that the property was satisfied, and the proof enabled us to understand the reason for the satisfaction. And finally, for the third property, we had a maybe value, so we could consult with the possible counterexample to understand why the property was not satisfied, and the possible proof that enable us to understand how to make it satisfied. So what we learned? So first of all, what we learned is that creating new instances of our framework is not easy. As you have seen, choosing or defining a semantics for a formula on partial model is not easy, and it strongly influences the model checking and the Turing improving techniques that can be used. So the selection of the model checker and Turing improving to be combined and must be done carefully to ensure the correctness of the obtained framework. And they also need to be changed and modified. For example, in our case, we had to modify the Zook palette framework to support triple structure, which was not the original modeling formalism which was supported. So what we conclude is we propose Thrive, we show an instance of Thrive that consider partial triple structure in level transition system, and we assess the effectiveness on manually developed and simulated experiments. When we finish this work, we basically understand that as a future work, we would like to integrate Thrive on the top of existing Turing improvers and model checker and to actually implement this. This brings us to the second work, which is called Integrated Topological Proof with Model Checking to Instrument Iterative Design, was done in collaboration with Alessandro Maria Rizzi and Anna Bernasconi. Essentially, in this work, we started by our original goal was simply to implement our solution. So we actually wanted to do a tool demo. We didn't want to do a fresh new paper. That was not our goal originally. So essentially, we had this really beautiful framework with model checking and Turing proven, with this no plus counterexample, yes plus definitive proof, maybe plus counterexample and proof, and we want to implement it. We wanted to implement it. And notice that the proof are deductive proof. What this means is they kind of apply some set of deduction rules until you have a proof that something goes. So we actually started and then a prototype implementation of this framework, but we quickly realized that we had a problem with deductive. So the problem is that for us, or for kind of non-experts, those proofs are usually difficult to understand. One of the reasons being, of course, you need a stronger mathematical background, but their size significantly grows with the size of the model to be analyzed. And this is exactly the problem we try to address in the second work. So our question was, how can we provide more effective support and guidance to engineer when the properties of interest are satisfied or possibly satisfied? So what we did is basically we went back and tried to simulate what the engineer can do in defining the model. So we changed our running example. We started considering vacuum cleaning robots with a set of requirements, a partial type structure, so preliminary model of the system. We started the verification procedure. Of course, some property are violated, some others satisfied or possibly satisfied. And we tried to understand what a developer can do. For example, during a revision, an engineer can add or remove states, add or remove transition, or change the values of some of the proposition. For example, in our robot example, the engineer can decide to change the value of the atomic proposition reached in the state idle and change it from maybe to false, meaning that the reached proposition is false in the state. And then we came up with this idea, the topological proof idea. So our intuition was the following. What if we are able to produce a slice of the model that witnesses the property satisfaction? Essentially, we have a model. If we are able to identify a sub-portion of the model that ensure the following property, so that if the engineer does not touch, does not modify the elements in the topological proof, then the revision will not violate the property. This might be beneficial. Essentially, we provide a size of the model and we tell to the engineer, change whatever you want. Don't touch anything that is in the topological proof. If you follow this simple rule, you are sure, you have formal guarantees that your property will remain possibly satisfied or satisfied, depending on the region system. And this is what exactly we did in this work. We propose a framework, which is called TOrPEDO, which supports the use of topological proof across the development of a software system. So essentially in TOrPEDO, there are two manual activity, the initial design, where the engineer starts providing a preliminary design of the system, and the revision, where the engineer modifies the model. And there are two automated components. The first one is the analysis component, and the second one is the recheck component. Now, the analysis component, it produces counterexample, as in try, or possible counterexample, but it also produces possible topological proof or topological proof, definitive topological proof, which are given to the developer as well. So essentially, those are slices of the model which are given to the engineer with the guidance, with the instruction. Don't change this part. If you don't change this part, the property will remain, the satisfaction of the property will remain as in the previous case. And essentially, we have a component which we call it recheck, which essentially is a simple syntactic check which checks whether the engineer during the revision followed the rules that were specified within the topological. So as I told you before, a topological proof is a slice of the model, and a topological proof is made by a set of clauses. What are these clauses? There are three types of clauses. The first one is a propositional clause. It basically tells the engineer to not change the value of some proposition in some of the states. For example, in this case, we are telling the engineer in the state cleaning, don't change the value of the proposition reach from its previous value, from true value. That's what a propositional clause is. It basically tells the engineer, don't change the value of reach to true from true within the state cleaning. That's a propositional, topological propositional clause. The second clause are transition from state clause. They basically identify a subset of the transition of the partial structure the engineer should not change. For example, in this case, the engineer should not modify the transition from the state move to the state moving and the state cleaning. So the two blue transition highlighted in blue in the left side of the slide. So essentially, they basically constrain the developer to not change a subset of the transition of the partial structure. And finally, we have the last type of clause, which are initial state clauses, which basically force the engineer to not change the initial state of the system. I mean, one initial state, it can be all the initial states, it can be a subset of the initial state, depending on how the extraction of on what the analysis component produces. So essentially, in this case, it tells the engineer, do not remove the state of from the set of the initial states of the system. And essentially, a topological proof is a set of clauses like the one presented in these slides, and essentially are slides of the model, like the blue component identified on the top right part of the slides. So on the state machine report and on the right part of the slides. As you see in the slides, all the transitions are reported in blue, meaning that all the transition should not be modified by the developer, but this is not the standard case. This was just a result that concerned a property that was considered in this specific case. But in general, you can have a subset of the transition highlighted in blue that you should not modify. So given those rules, an engineer can modify the system by following a set of revision rules. So she can add or remove transition for which the source states is not in the transition included in the topological proof transition clauses. She should not change the value of the proposition in the topological proof propositional clauses. She can remove states if they are not in propositional clauses, transition clauses or initial clause, or change the initial states of the system by following those rules. So the main idea is that if the engineer follows the revision rules, then the revision will not violate the property. So the satisfaction of the property is preserved. For example, in the previous case, we have the initial model, the components involved in the topological proof highlighted in blue, and the engineers already know by definition that she can change the value of the proposition reached within the state idle from maybe to false or true without actually influencing the satisfaction of the property. For example, in this case, she changed the value of the proposition reach to false, so the bottom value. So how does the magic work behind the scenes? So how does the framework, the automated TOrPEDO works in terms of automated support? So there are two components. The first one is the analysis component. The analysis component essentially relies on three steps. First, it encodes the model and the negation of the property using the system to LTL component into a set of LTL clauses. Then once you have the set of LTL clauses, it uses a PLTL loop to get the answer code. Actually, to be more precise, we use a specific instance of PLTL loop in our experiments, which is called TRP++ UC, which is improve actually the performance of the answer code extraction. Once we have the LTL conflicting clauses, we take those clauses and we trace them back on the original model. So we extract the topological proof propositional clauses, transition clauses, and initial state clauses with the get topological proof component, which finally returns the topological proof to the users. So the second component is the recheck component. The recheck component is a naive component that basically statically analyzes the partial key structure, and it basically verifies that the engineer did not add or remove transition, change the value of the proposition, or remove states, or change initial states of the system. So essentially, that would, of course, were involved in one of the topological courses. Essentially, it statically checked that the engineer didn't change any element which was involved within the topological. So having implemented the framework, we actually move to our evaluation. The first research question we have is, how does the size of the proof computed by the analysis component compare with the size of the original model? Essentially, the intuition here is that we want to analyze how big are the topological proof with respect to the original model. Because the smaller the topological proof are, the easier our conjecture is that the smaller they are, the easier they are to be interpreted by the developer. So we consider 60 model requirements combination, 12 model partial key structure, 5 properties for each model. We run TOrPEDO, and we compare the size of the topological proof and the size of the original model. Our results show that topological proof are approximately 60% smaller than the corresponding model. So this is a significant improvement in terms of what the developer and the engineer should check and consider during the development of the system. The second question we analyze is how does the recheck component support the creation of model revision? So what we did is we considered 3 models and 5 properties per model, and for each model we developed for revision. We ran TOrPEDO, we computed the topological proof, and we computed the percentage of cases in which the recheck component was useful, meaning that the recheck component simply tells, okay, you know what you did was compliant with the topological proof. You did a good job. You followed the rules of the topological proof. And it actually turns out that in 78% of the cases, the recheck component confirmed that the revision was compliant with the topological proof. And this is a significant benefit since first, we show that the engineer followed the rules, and that in many cases, actually, you don't need to rerun the analysis component from scratch. You can just run the recheck component. So our final question was, what is the scalability of TOrPEDO? How does TOrPEDO scale? So to have a ballpark estimation of the scalability of TOrPEDO, we assess its performance on the model we consider for research question 1 and research question 2, and we manually designed an additional model, which was relatively bigger than the other one. It had 10 states, 5 atomic proposition, and 26 transitions. So this model is, however, still pretty small. So for the model from research question 1 and research question 2, actually, to compute a topological proof, a TOrPEDO required less than 10 seconds. However, for our additional example, which has still few states, the topological proof was computed in 1 minute and 33 seconds. So, and this on a partial key structure with 10 states and 20 transitions. So what we concluded? So in this work, we proposed TOrPEDO, a framework that supports iterative model design. We defined the novel notion of topological proof, and we evaluated TOrPEDO by assessing the support provided by the analysis and the recheck component, as well as try to have an understanding of the scalability of the technique. The result shows that the proof are smaller, 60% smaller than the model. Revision actually can be verified in 78% of the cases by running a simple syntactic check. However, we were not satisfied with the scalability. Actually, we believe that the scalability of our technology is not sufficient when you try to move to practical application. So we ended up this work and we say, you know, as a future work, we need to develop more efficient procedure to extract the topological proof, which was actually the bottleneck of the project of our solution. So this is exactly what we tried to do in the following work, which was published in Formal Aspect of Computing in 2021, which is called TOrPEDO. This work has been done again in collaboration with Alessandro Maria Rizzi, Anna Bernasconi, and also Paola Spoletti. So essentially, in our previous work, we tried to implement a TOrPEDO using USMV as a model checker and PLTL-MOOP to compute a minimal subset of unsatisfiable LTL formula. I will refer to this version of TOrPEDO in this presentation as TOrPEDO-MOOP, where MOOP is basically a shortcut for PLTL-MOOP. Essentially, if you remember how the procedure works, PLTL-MOOP is the component highlighted by the arrow, and it's basically used to extract conflicting clauses from LTL clauses. And our question and our problem for this work is, can we reduce the computational cost required to compute topological proof? So our contribution. So what we did is we proposed TOrPEDO SMT. Essentially, the main idea of this work is to try to reduce LTL formula into an SMT proper. And we use existing technology to actually convert LTL formula into an SMT proper. And specifically, actually, our solution relies on a recent encoding, which relies on bit vectors. And according to the author of these two papers, is much more efficient than existing solution. So essentially, we convert, in these slides, we present our previous solution, which is PLTL-MOOP, is on the bottom slides of the get answer core component, in the bottom part of the get answer core component, and on the top part, we have TOrPEDO SMT, just to have a visualization of how the different approaches work. For TOrPEDO SMT, it basically works in 3 steps. The first step is the LTL to propositional logic converter. It takes LTL formulae, and it translates them into propositional logic. Essentially, it unrolls the LTL formula up to length k, up to a bound k. The second component is called the get answer core component, or it basically computes the unsatisfiable core of a propositional formula, and we actually use Z3 to compute the unsatisfiable core. And the third component is the propositional logic to LTL component, which takes the conflicting propositional clauses and it debates trace them back on over the original LTL formula. And our conjecture is that this solution is more efficient than the original solution. So what we did in our evaluation, we tried to understand how efficient is TOrPEDO in analyzing model, and specifically, how does TOrPEDO SMT compare with TOrPEDO-MOOP? We generated a set of random models with increasing number of states, starting from 10 to 20, 30, and 40 states. The models, of course, are generated from an existing example, the grade crossing semaphore example, and we consider 2 properties which are respectively satisfied and possibly satisfied. We run TOrPEDO-MOOP and TOrPEDO SMT. Remember that for TOrPEDO SMT, we need to select a value for the bound k. We set the value to 86 by consulting existing research literature on the topic. And for our experiment, we set 2 hours as a timer. So these are our results. So for TOrPEDO-MOOP, the results are represented for property phi1 with the blue line. For the property phi2, they are actually represented in orange. Actually, there is only 1 point related to property phi2, which is exactly from 10 states, meaning that TOrPEDO-MOOP for property phi2 could not produce a result even for 20 states within 2 hours. So there is only 1 bullet point in this graph for TOrPEDO-MOOP for property phi2, which is represented in orange. For TOrPEDO SMT, actually the results are reported for property phi1 in yellow and for property phi2 in purple. So essentially what the answer to our research question is that over the considered model, TOrPEDO SMT can verify within the timeout models which are double in size compared to TOrPEDO MOOP, meaning that TOrPEDO MOOP can analyze model up to 20 states, while in 2 hours, TOrPEDO SMT was able to analyze models that reach 40 states, so double in size. For the cases in which when both the tools finished within the timeout, TOrPEDO SMT was significantly faster than TOrPEDO MOOP. TOrPEDO SMT required on average 1.5 minutes for basically 10 and 20 states. TOrPEDO MOOP, on the contrary, required on average 15 minutes. So TOrPEDO SMT was significantly faster. We also consider an additional research question, which is how useful is TOrPEDO SMT in supporting design and in the model design activity on an example in the genomic domain. The main reason is that basically Anna Bernasconi, she moved into a database community where she's working on the genomic analysis of database. So we have know-how of this on this specific example. So we consider a small model from the genomic domain, which concern regulatory networks, which are basically collection of molecular regulation, and explain how these regulators interact with each other. So we basically use a partial key structure to represent the status of the genes by using the atomic proposition. Basically, an atomic proposition is true if the gene is activated. The states, they describe the status of all the possible genes. At the end, we have a partial key structure with 64 states, and the transition encode basically how the status of the gene can change over time. And of course, we have this is a partial key structure because at the beginning you don't know how the value of the gene change over time. We consider 2 LTR properties from the literature discussed with domain expert. We simulated an incremental model design with TOrPEDO. So essentially, we consider 3 properties and the 5 models here: the initial model, revision 1, revision 2, revision 3, and revision 4. So we evaluated 3 properties. Actually, for our analysis, we had to run the analysis 3 times on the initial model, on the revision 3, and the revision 4 of the model. Actually, for 2 models, for 2 versions of the model, we could use only the simple syntactic check. So we use the syntactic check twice. So we concluded actually with that topological proof provided useful information. And of course, during the design of the revision, we consulted the topological proof to decide what to change in the model revision and so on and so forth. So the answer to research question 4 is that topological proof and counterexample provided by TOrPEDO effectively supported the development of a partial key structure for our example of the gene regulatory network. So the reflection, of course, our algorithm, the version of TOrPEDO SMT, is correct if the LTL clauses extracted are actually contradicting. And as you probably may have guessed, the correctness depends on the value that is selected for the bound K. If K is higher than a threshold, which is called completeness threshold in the literature, then the LTL clauses are contradicted, otherwise you have no guarantee. And of course, you can consult existing research literature to decide how to set the value of K for the different models and the different scenario. What designer can do in practice is initially choose a value of K that is reasonably large and increase and decrease the value depending on the efficiency and the analysis and the importance of the soundness of the results for the specific domain. Of course, there are why our solution is faster. Of course, there is a difference in the complexity class between TOrPEDO MOOP and TOrPEDO SMT. And also one of the benefits of our solution is that we rely on Z-free. So compared to a PLTR MOOP, Z-free is an industry strength tool. It was awarded by ETAPS with the Test of Time Award, the ACM SIG Plan Award. So there is a large community behind Z-free. So our results with TOrPEDO SMT are likely to improve more significantly over time than the results obtained by considering TOrPEDO MOOP. Okay, After we finish this work, I would like to discuss a work which appeared on 2023, which is called Trace Diagnostic for Signal-Based Temporal Properties. I will not enter into the detail of this work. It will take me 5 minutes. This work has been developed in collaboration with Shaima Bufaye, Domenico Bianculli, and Lionel Green. So let's see what the problem is in this case. We have a system, we run our system, and we have an execution trace. We have a set of requirements which are formalized as a set of properties. So essentially, we run a trace checking algorithm. So given a trace and the property checks whether the property is satisfied or violated by the trace. And imagine we are in the situation in which we have a property violation. So essentially, the trace violates the property of interest. Now, our question is, why is violated? Can we support engineers in understanding what is the source of the violation? So essentially, our problem is, how do we explain why a property is violated by a trace? Can we support this process in some way? So the contribution of this work is called TDS-VTEMSI, is the trace diagnostic approach for signal-based temporal property. Essentially, it analyzes a trace and a property which is violated by the trace and provide an explanation for the property violation. SVTEMSI relies on two elements. The first one is violation causes, and the second one is diagnosis. So violation causes, they basically characterize one of the possible behavior of the system that may lead to a property violation, and diagnosis or information associated with the property violation. What I want to focus my attention on in this presentation is violation cause. Essentially, a violation cause is a formula that satisfies the following relation. If the violation cause holds, then the corresponding requirements should be violated by the trace. And I want to make a parallel. On the top part of the slides, I have the notion of topological proof. So a topological proof is a slice of the model that witnesses the property satisfaction. So if the topological proof is satisfied, then the property will remain satisfied, more or less. On the second part of the slides, I have the definition of violation cause. A violation cause is a construct that if it's satisfied by a slice of the trace, so it characterizes a slice of the trace, so if it's satisfied, it witnesses the property violation. As you see, there is a strong relation, at least from a high perspective, conceptual perspective, between topological proof and violation clauses. Of course, they work on different artifacts. A topological proof works on models, a violation cause works on traces, and they witness different elements. The first one witnesses the property satisfaction, the second one, the property violation. In the paper, then, we describe our trace diagnostic, SVTEMSI, the trace diagnostic approach, the methodology to define violation causes and diagnosis, which provides formal guarantees on the soundness of the violation causes, a catalog of violation causes, and most importantly, we evaluated TDS-VTEMSI on 2 data sets, including one coming from an industrial case study. Essentially, our data set includes 361 traces, 98 requirements for a total of more than 30,000 trace property combinations. And by considering those combinations, actually, our results showed that TDS-VTEMSI was able to compute a diagnosis within a timeout for 83% of the combination. And this basically ends up the list of papers I want to discuss. Let's start with the part related to the reflection, lessons learned, and some of my speculation. So my first reflection, which actually I also presented on some additional other talks, which I recently done, is that there is a synergy. I believe there is a strong synergy between theory and practice. Theory needs practice, practice needs theory, and vice versa. And this is, I think, really nice example of research, because we started with a theoretical framework in 2017. Remember that in 2017, in our evaluation, we even didn't have an implementation. We perform our evaluation fully manually. Then in 2020, we actually tried to implement the solution. We found some problems, so we modified the solution. And we realized that even the modified solution has limitation on the efficiency. Then in 2021, we work on the improvement of the efficiency of the proposed solution by reusing SMT solution. And finally, in 2023, we were able to kind of customize the existing solution from a problem coming from the industrial domain and actually have some significant result also on a data set which was provided by the industrial partner. And I believe that this is a really strong result from the formal methods community, showing how we can move from something which is really theoretical for something that works in practice. The second reflection I want to make is that, of course, these results are teamwork. I significantly acknowledge all of my collaborators, Bernasconi Anna, Alessandro Maria Rizzi, Domenico Bianculli, Sharma Buffet, Paolo Spolettini, Carlo Ghezzi, Leonard Duck, and Lionel Briand. And specifically, I would like to spend a few additional work on Anna Bernasconi and Alessandro Maria Rizzi. They were fantastic collaborators for the FACS 2020 paper, for the formal aspect of computing 2021 paper. Actually, Anna was the first author in the 2017 paper, but I believe that at that point, we weren't aware about the possibility of adding a footnote and adding all the author as a first author, but they should be considered, and they must be considered as first author of this paper because they did a fantastic job and extreme job here. My third reflection, I think that some of the reviewers significantly helped us in improving our papers, our paper over time. I would like to acknowledge and thank one of the reviewers, which is the reviewer 3 of VMKI 2019, which actually rejected our paper. And she or he rejected our paper for a really good reason. So in one point of the paper, we were mentioning that we were constructing an LTL formula which was equisatisfiable. And indeed, the review was completely correct. These conditions were not sufficient to guarantee the correctness of our framework. Actually, it was a typo, our mistake in the paper. The formula was not equisatisfiable, it was equivalent, but I believe that the reviewer did a great job in spotting this error, and I would like to thank this reviewer because I believe she or he significantly helped us in improving the paper. Now, my final remark, which is a question. So did we reach the Independence Day of witnessing the correctness of the system, which is kind of the title of the presentation? Well, no, I don't. I think there is a lot of work to be done. I think we are still not there. We didn't reach the Independence Day for witnessing the correctness of system. Specifically, there are many challenges that remain to be open. First of all, there are a lot of formalists out there, modeling formalists, and as you have seen, adaptive thrive and existing solution to new formalists is complicated. It's complex and complicated. There are different difficulties on how to integrate existing theory improving and model checking. The second one, there is a variety of requirement specification languages. For example, in our case, we consider LTL formulae, but there are CTL formulae, there are probabilistic formulae. So there is a lot to be done to also cover those additional languages. Of course, there is a trade-off between expressiveness and performances, or actually between the semantics even and the performances and correctness. As you have seen in our work, we have seen the difference between self-minimizing, the three-value semantics and the four semantic. We have seen that the three-value semantic offers some benefits in terms of expressiveness, but on the other hand, it has some cons in terms of correctness with respect to the four semantics. And of course, there are expressiveness and performances should be deeply studied. Then we are the question of how to develop techniques that are complete and correct. As we have seen, TORPEDO SMT, for example, depends on the value that we select for the value k. Depending on the value we use and we choose for the value k, we can have a solution set of LTL clauses which are indeed conflicting and contradictory or not. So completeness and correctness are two challenges for developing witnesses for model. And finally, there is a last challenge, which is how to develop techniques which are usable for end user. So to conclude, I believe that reaching the Independence Day of witnessing the correctness of system is a journey. So everyone is invited to join this journey. There is a lot of work to be done, and I hope everyone enjoys the trip. And this basically ends up my presentation, and I open up the floor for questions from the audience.
Thank you, Claudio. It's very interesting. There are a few questions on the chat, so I think we should start with that because they've been there for a while. I can read them out if you want.
Yeah, let me maybe stop sharing the screen then. Do you want to read them out?
Yeah, let me see. Let me find them here. Okay, so the first one by Tianxiang. How do you handle the state exploration problem of the model checker in your architecture as the first component? Do you set a time or step thresholds to stop the program?
So for the model checking part, we fully rely on USMV. So essentially, we completely rely. I mean, it depends on which of the three works you are considering. So in the first work, it's a fully theoretical work, so there is no implementation. In the second and the third work, we basically completely and fully rely on USMV. Okay.
Okay, so there was another question. Is infinite models or infinite state space of the variables considered in your approach? In a finite state machine, you basically have a decidable subset of problems. I can fully understand your approach to work well with partial models. However, I can't see how it works with infinite state space.
Yeah, our assumption, that's a really good question. Thank you for the question. Our assumption for this work is that the models are finite state models. So we do not handle infinite state space models of the system.
Okay. Then Margaret asks, can you split theorems into parts if, for example, paths are complex?
Can I just add, what I really meant was, are they decomposable or composable? This is completely new, the idea of this, so it might be a silly question. So are they composable or decomposable, these topological
That's a great question for which I have no answer. So my speculation is that if you have a topological proof, I guess it depends if there are, I have to reason about this. So I speculate that, of course, understanding if they are composable or not is something I cannot answer, but probably they are, or there are ways in which we can compose topological proof. On the other side, I think that the problem is how to compute a small topological proof, not how to compose them to have a bigger one. Or maybe the question is, how can I compose two topological proof to have a smaller one? If there is a way to basically compose two topological proof and getting a composition which is smaller than the initial proof. That's, I think, because one of your goals, you want your topological proof to be as smaller as you can, because the smaller they are, the easier they are to be interpreted.
What I really meant was, supposing you want to, you've got a system composing, I don't know, so many states, half a dozen maybe, and then someone says, oh, but we want to do this as well with some more states.
Yeah, that's a great question. So you mean we have two components maybe running in parallel?
Yes.
A topological proof for one component and a topological
or in parallel or in sequence. Sequence, I suppose, is easier than in parallel.
Yeah, that's a great question. I have no answer for that. I think that's a great direction for future work. Yeah.
Yeah.
Because this may also actually, understanding the composition maybe can provide a way to decompose the system from the beginning and maybe compute even smaller topological proof. Yeah.
Whatever. Anyway.
Okay, so another question was by Tianxiang. Interesting perspective with topological proof. How do you find the topological proof? Do you use any SAT solvers to verify the proof or SMTs, or do you do it manually?
I mean, to verify the property, to verify the topological proof, it's basically a simple script, because we go on each clause one by one, and it's an if-then. So you take the clause, you look at the model, you see, is this change or not? So it's basically, I don't know, 20 lines of Scala code, maybe, and you just take one topological, you do a for loop over the different clauses, and for each clause, you check if the model, if the clause has been changed, if the corresponding element in the model has been changed or not. So we didn't rely on any SAT solver technology for the recheck component.
Okay, maybe rephrase my question. So I've seen that basically the question was phrased actually before you have talked about your SFT approach. So that was basically the idea. You have found a topological proof. So for verifying that your topological proof is effectively correct, I mean, for the finite model, there's no need for such kind of a thing, but it only really makes sense for infinite models. So basically the question are interlinked with each other.
Yeah, for infinite models, we do not support them at the moment.
Yeah.
There is work that kind of, for example, generates finite state machine for model transition systems and how to translate them on partial Clipper structure. This, in principle, we could support it, but it's still a finite model. So we have a finite model and we analyze it. I have no idea, and actually that's a really great question, how this framework extends, can be used and modified to infinite models. Even if, because we assume we have these LTL clauses. So if the system is infinite, the first question I have is, how do you get these LTL clauses as a starting point? I have no answer for this. Probably there is, it's kind of research. It's an interesting research direction.
Yeah, so yeah. Thank you for your answer. Maybe the next one is also from me. I was a bit confused with the statement always to hear about witness property satisfaction. So when I hear the word, well, you have found a witness for satisfying property, for me, it is not sufficient as a proof for the safety property. For me, it's only a proof for the safety property if you can find a witness of the counter example. So you find a witness basically on the property's negation, not on the property itself. So it's a little bit confused for me to understand your intuition on saying, okay, we have a witness of property satisfaction. So how can I understand that?
Yeah, in this work, our witness is basically a proof. So you have a system and a property that holds, and you want to have a proof. That's how we basically consider the witness in this specific work. I agree with you, there are different definitions of witnesses. One is the one you basically mentioned, which kind of relates to this specific type of witness, but I would say there are different artifacts and different types. Yes, but you're right, there are many different type of witnesses within research literature. Yes, and one of them is the one you were mentioning.
Yeah, so that makes sense. So witness, okay, if it is a proof, then it's fine.
It's, yeah, we kind of started with, I mean, by looking at the timeline of the work, we started with this idea of deductive proof. That's where everything started. And then we started implementation, and then we realized deductive proof, and then we came up with the notion of topological proof, which essentially relates to what you mentioned, is a different artifact. Now the question, which of the two artifacts is more effective? I think we need end user to understand. And I think it probably also depends, right? In the stage of the development and so on and so forth, in the user that you analyze. So.
Any other questions?
Claude, if I may ask you a more direction of a research kind of question. I've been following the work you've done, because you've done some very beautiful work, and I've been very interested in your work in robotics as well. So I've been wondering about two things. One is whether you have plans to apply this approach to any applications in robotics, like the ones you've worked before with human interaction, particularly interesting. And of course I've seen some of your work in PRISM, and I think these partial models and probabilistic models are capturing different forms of uncertainty. If you have thought about bringing these approaches together, those are my two questions. How do you view this going forward in robotics in particular?
Yeah, I guess that, so we have some experience with this theoretical trial framework and how to customize it. So all the direction you mentioning are something which in general I feel they are interesting, and it's something I definitely have interest in pursuing over time and following up over time. Of course, as you know, doing good work requires time, and so at some point we need to prioritize. But I think that my plan is to start working on the direction, or I am interested in the direction you were mentioning in your question. Now, I'm not actively working on those at the moment, but they are definitely good and interesting future work to be explored. Yes. So I would like to thank BGS FACS for the invitation. It's been a pleasure to be here to provide this presentation. It was an honor, so I thank Alvaro and the other BGS FACS organization team to put this meeting in place. Thank you.
Thank you very much for the presentation, Claudio. It was really interesting.
Yes, thank you, Claudio. Great.
Thank you.
Thank you.
So if there's nothing else, I think we can close the meeting. Yeah.
I'll stop the recording.
Okay. Thank you.